So when we use a linearization, when we use any kind of approximation, any kind of method for making an approximation, any information we can give about how good or how bad our approximation might be, or which direction it is our approximation going to be too big or too small? The more information we can give like that, the better we can understand the limits of our approximation and make sure that we use it appropriately. So to understand how a linearization might be different from the actual function value we were hoping to find, we want to take a look at these 4 graphs. There are 4 different behaviors, combinations of behavior that a function might have over some interval. This function might look, this first function top left corner might look like that might be the whole function, or that could just be one teeny tiny part. But we're going to examine what happens, on whatever kind of interval you need until the concavity or the increasingness or decreasingness changes. A function could be concave up and decreasing, like the top left corner, or it could be concave up and increasing, like the top right corner. Remember, concave up looks like a bowl. Where's my... There we go. Concave down looks like an umbrella. Or a function could be concave down and decreasing, or concave down and increasing. So 4 possible combinations, and we can see what happens with the tangent line for each of those possibilities. So you can see here. So in each of these cases, the curve is drawn in red, and the tangent line to some made-up point, x equals a, is drawn in blue. So for the top left corner, the tangent line is below the actual red curve, which means that if I use tangent line values to approximate the curve, I'm always going to have an underestimate, except for right at x equals a, where I'm going to have exactly the right value. Similarly, where my function top right corner is concave up and increasing, I'm going to have the tangent line lying below the curve. The bottom 2 possibilities, when the function is concave down and decreasing or concave down and increasing, my tangent line lies above the curve. So here's my curve, and then the tangent line lies above it. So if I wanted to use the linearization to approximate a value on the function, my estimate is always going to be an overestimate. So if we look at it this way, we can conclude that whether your tangent line is an overestimate or an underestimate depends on the concavity of your graph. So that is an important note that goes in your notes paper here. So from the pictures above, we conclude that the linearization L of x of a function f of x overestimates f of x on intervals where f of x is, overestimates on intervals where f is. Give an approximation using a linearization, and then say something about whether that approximation is going to be an overestimate or an underestimate. So here we go. I have a function f of x. I know some values of f. I know some values of f prime. I've been asked to write the equation of line tangent to f at x equals 1. So right here they've told me what my a is going to be. To use this to find an approximate value of f of 1.2, notice there's no way I could tell you exactly what f of 1.2 is, because 1.2 isn't one of the x values for which f has already been evaluated for me. And then to say something at the end about whether that approximation I gave is an overestimate or an underestimate. So I don't happen to memorize that formula from the yellow box. I start with point slope form every time. So I know I'm going to use an ordered pair 1, comma, these are supposed to be points on the a point on the f function, so 1, comma, -4. The slope at 1 is, I'm going to use f prime, so I'm going to use m is 5. So I'm going to write the equation for the line tangent. That's going to be y plus 4 equals 5 times x minus 1. So I know y is -4 plus 5 times x minus 1. If you wanted to get fancy, you could name that function L for linearization. L of x is going to equal -4 plus 5 times the quantity x minus 1. Maybe in your Algebra 1 class or your Algebra 2 class, you spent lots of time simplifying that expression on the right-hand side to change into slope-intercept form. I'm here to tell you that the math that you're about to be asked to do is going to be easier if you do not distribute. So just consider not messing with that function now. Watch how easy the calculation becomes. Once I have this, well, this is the equation of the line tangent. I definitely want to use x's and y's there because that's how I'm expecting to find the equation of a line. Now that I can use that tangent line, or this version that I wrote that I called L of x, to approximate f of 1.2. Well, f of 1.2 is going to be approximately equal to L of 1.2. So I'm going to find L of 1.2. That means I'm going to replace all the x's in the L. -4 plus 5 times 1.2 minus 1. I'm going to simplify inside those parentheses first. 1.2 minus 1 is 0.2. 5 times 0.2 is 1. So this is going to be -4 plus 1. F of 1.2 is approximately equal to -4 plus 1. You could simplify to -3. Notice that if I had distributed that, I end up doing more math with more decimals. So please consider leaving this not distributed and simplifying that expression first. All right, so I have one more part, and that's to say whether my approximation, which is -3, is an overestimate or an underestimate of the actual value of f of 1.2. So I have to examine, in order to answer that, I'm going to have to examine the concavity of f. Well, what do I know about f? The second derivative has the property that f double prime is positive. Well, we just found out in the last video that we did that if f double prime is positive, f double prime of x is positive, means f is concave up. So I'm going to draw myself a little picture. I actually draw this picture all the time, or I use my fingers to make concave up and then find out that if I was going to draw the tangent line, that's underneath. So here's a picture that's concave up. If I try to draw the tangent line to it, my tangent line lies below the curve, which means my tangent line approximation, my linearization, is going to be an underestimate. So I'm going to say f of 1.2 is approximately equal to -3 is, I'm going to type this out. All right, so here's what I wrote up. F of 1.2 is approximately equal to -3 is an underestimate of the true value of f of 1.2 because f double prime is positive on that interval. I use the interval that they gave me here. The interval I give here just has to be big enough to include the original a value, which in this case was 1, and the x value at which I care to have an approximation. So here I just borrowed these numbers because they told me that f double prime was positive on that whole interval. I could have just said because f double prime is positive on the interval 1 is less than x, which is less than 1.2. But that interval that you know the concavity, it has to extend to include both the original a and the x value that you want an estimate at. Final answer.